Hello, this is Math 2134 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Differentiation Tradecraft Theorems 1. Please engage actively in this video. When last we left, you were working on this problem, and maybe you finished and maybe you got distracted, so I'll give you a little bit more time to do it. What we were doing is we were finding the derivatives of the function given in A and the function given in B. You know what to do. Let's see how you did. Well, the derivative is, you can pull the constant through the derivative, so it's 5 times the derivative with respect to x of x cubed, which is 3x squared. You do all the calculation, and the simplified answer is 15x squared. Here, in part B, what you do is you write this as a fractional exponent, and it's going to be 3x to the minus 1/2. You jerk the 3 through, then you take the derivative of x to the minus 1/2. That is going to be minus 1/2 x to the minus 3/2 when you subtract 1, and you could write that this way because the minus has it in the denominator, has the variable in the denominator. The next theorem, or rule we'll talk about, is the sum rule. Now, just as we could say that the limit of the sum or difference of two functions is the sum of the limits of the two functions, or the difference of the limits of the two functions, and since the derivative is the limit, this happens. So, in words, the derivative of the sum or difference of two differentiable functions is equal to the sum or difference of their derivatives. This can be said another way. You can do the derivatives term by term, and what separates terms are plus or minus signs. And this result can be extended to the sum and difference of any finite number of differentiable functions. And let's look at the proof of this. And so the sum is the sum of the two. S of x is f of x plus g of x. So we do that, we get this, but then we can rearrange this. We can put the minus x over here with this one, and the when I distribute here, I get a minus g. Also, so I'm putting that over here, and then I can do the limit of the sum of the limits, and I can do the derivatives term by term. Here's an example where you can do two problems, and we'll see how you do. It says find the derivatives of these two functions. You know what to do. Let's see how you did. Well, I'm doing it term by term, so I'm going to take the derivative of this 4x to the 5th, the derivative of 3x to the 4th, the derivative of 8x squared, the minus sign got factored through already, and the derivative of x, and the derivative of a constant. I'm doing it term by term. So this is going to be 5 times 4 is 20, x to the 4th. This is going to be 4 times 3, x cubed. This is going to, the minus sign just sits there. This is going to be 16 x, subtract 1 from the exponent, you get that, and there's an automatic 1 up there, so the derivative of that is just 1, and 3 is 0. Here the independent variable is t instead of x, so you're taking the derivative with respect to t. Notice that here we just call it g prime, and we do it. Now here what's going to happen then is we do it term by term, so it is 2/5 t to the 1. And here it's going to be minus 15t to the minus 4. I can write this way, and I could also get a common denominator if I cared to. Here's a very common problem. If you tell someone you took calculus, they will say, well, of course you know how to find the equation of the tangent line to a curve at a given point, and that's exactly what this problem is asking you to do. You know what to do. Let's see how you did. Okay, well, the slope of the tangent line is given by the derivative at that point. And so we take the derivative with respect to x of the function. We write it this way, and we take the derivative. The derivative of 2x is 2. The derivative of x to the minus 1/2 is minus 1/2 x to the minus 3/2, and we can rewrite it this way. In particular, the slope of the tangent line at 1, 3, and again we take the 1 because this is a function of x. We plug 1 in there and we find, after calculation, that the slope is 3/2. Then we've got a point, which was this one, in the slope, so we can use the point slope form of it. So it's y minus the y coordinate is equal to the slope times parentheses x minus the x coordinate. And you can simplify that if you cared to write it this way. This is what the graph looks like. So you see the blue curve was our original function, but we were finding the equation of the tangent line, and you see it kisses the function here at 1, 3. Life is a word problem, and so we will do a lot of word problems in this course. So here's some of the words. A group of marine biologists at an institute recommended that a series of conservation measures be carried out over the next decade to save some species of whales from extinction. After implementation of their measures, the population of this species is expected to be, and you see they're saying a cubic approximates it, over these 10 years, where T denotes the population at the end of year T. So you want to find the growth, the rate of growth of the whale population when T is 2, when T is 6, and how large will the whale population be 8 years after implementing the measure. You know what to do. Let's see how you did. So the rate of growth, the rate of change, of course, so the rate of growth is going to be the derivative. So you take the derivative of this, you get 9 t squared plus 4t minus 10. And they ask you to plug in 2 and 6. So this is 34 whales. At the end of the rate of growth is 34 whales per year. And here the growth becomes 338 whales per year. And that's just saying this after 2 and 6 years. And then at the end of 8 years, though, you're taking the 8, but you're plugging it into this equation because they ask about what was the population, not what was the rate of change of the population. And this is what the graph looks like, and you see it really starts taking off. So assuming they do this, this would be good news for the whales. Here is another word problem, and this has to do with the altitude of a rocket. Again, this is a very fundamental thing. And a rocket lifts off vertically. Its altitude in feet, t seconds into flight, is given by this equation. Now, it is important that you realize that they're talking about distance here, and this is distance of the height. This is telling you that. So this is displacement. They're asking you to find an expression, v, for the velocity. And remember, we talked about velocity is the derivative of displacement with respect to time. They want you to find the equation for the velocity at these points, and using the results from the solution to part B and the observation that the highest point in its trajectory, the rocket's velocity is 0. You see it's going up and then it's going down. So assuming it's a continuous function, which it must be, it's going to be at 0 when it changes from going up to going down, and that will be the maximum point in its trajectory. So you want to find the maximum altitude. You know what to do. Let's see how you did. So, and here's a picture. It's going up and then it's going down, and you see that the slopes of the tangent lines here would be positive. The slopes of the tangent lines here would be negative, and so the slope of the tangent line at the top is 0. So when you take the derivative of this function, you should have gotten this expression, and you can plug all those numbers in they ask you to, and by the way, that's something I will tend to do. I'll ask you to plug in numbers, so this is a good exercise. You should get those values, and that's really what it's all about. Let's see. Oh, when is the velocity 0? We're going to take this equation, which is the velocity, and set it equal to 0, and solve. And so that tells us that happens at time t equals 64. And it is instructive. You really should solve this velocity equal to 0 and find that t is 64. It also will tell you that's, yeah, t is 64 is when it will be, the velocity will be 0. But then you take the 64 and you plug it back into the function that tells you the height, and you do the calculation, and there is your answer, and that is feet. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.